me. Here we go.
There's no facts or anything. We still got 25 minutes of this.
Wowie zowie. Wowie zowie.
The rich diversity of landforms and geologic activity on Earth make it unique in our solar system. 3 decades of space exploration have taught us that most of our neighboring planets are geologically stagnant when compared to the dynamic Earth. Until very recently, geologic phenomena such as earthquakes, oceans, volcanoes, and radiation were thought to be unrelated aspects of nature. But in the 1960s, Earth scientists had a bold and revolutionary realization that completely changed our concept of the Earth. They surmised that these diverse geologic phenomena could be explained by a single unifying concept, a blueprint of global geologic activity called the theory of plate tectonics. Plate tectonics is built on the premise that the outer skin of the Earth is composed of individual slabs, or plates. These rigid plates, which is continental in size, and in some places hundreds of kilometers thick, slide around on a partly molten vertical layer below. Where the plates collide, or move apart, or slide past one another, a great variety of geologic activity results. Oceans open and close, mountain belts emerge, and volcanoes erupt, all accompanied by countless earthquakes and the formation of new rocks and landforms. Although we still have a great deal to learn about the mechanisms in the Earth's interior which cause plates to move, most scientists agree that the concept of plate tectonics is valid.
Today, the theory of plate tectonics is widely embraced, but the road to its acceptance was long and at times fraught with controversy. During the 15th century, Europe began its great age of exploration. As navigators charted coastlines the world over, scholars became intrigued by the similarity between the Atlantic coasts of Africa and South America. In 1912, scientist Alfred Wegener introduced his theory of continental drift, which sought to explain this similarity.
Alfred Baker is one of the individuals who in the 20th century had a major influence on geological thought. He observed, like several before him, the geographic relationship along the Atlantic Ocean and the obvious match between particularly the African and South American continents. This led him to conclude that the surface of the Earth, these continents, were not stable but perhaps mobile, and led to his idea of distant continents. The kind that is not accepted, and it's not well accepted in either geological or other scientific thought, but ultimately laid the foundation for what was a real revolution in development.
Wegener pored over geological maps, discovered identical rock types, fossils, and mineral deposits in many different lands. He was intrigued by what he discovered. He began to see that certain patterns matched up with the stereo across major ocean basins, particularly in southern hemisphere continents.
Oh,
What we
no.
now call Gondwana, which is split apart into Antarctica, Australia, South America, and Africa. What he found is that certain plant fossils matched up very nicely on these different continents. He found certain climatic zones, glaciation zones, or coal bed zones matched up on these various continents. And they didn't make sense with where the continents are today in terms of the current climatic zones. When he put Africa against South America, Wegener discovered that the rocks of a South African mineral belt coincided with similar formations in Brazil. The South African mountain range, ending at the coast, lined up nicely with a similar range in Argentina. Furthermore, the areas of ancient rock in Africa formed a continuous belt with those in South America. Wegener wrote, "It is just as if we were to refit the torn pieces of a newspaper by matching their edges and then check whether the lines of print run smoothly across. If they do, there is nothing left but to conclude that the pieces were in fact joined in this way."
So Wegener really put together the story for all the continents and wrote it down and collected all the evidence that he could about it. And so that's partly why we hear so much about Wegener, because he brought it all together.
Wegener's suggestion that the continents had once been joined and drifted apart to their present positions ignited a major controversy in the scientific community. Acceptance of Wegener's continental drift theory seemed to be divided roughly along hemispheric lines.
I think the geologists who were working in the southern continents never had any doubt, because the evolution of species is so clearly parallel on them. And you have so many other geological events that are in common between South Africans and South America and India and Antarctica once we began to explore it. There's just no doubt that they were all part of one piece. But most geologists weren't working in the southern continent, they were working in Europe and North America, and they didn't have time.
Many scientists were especially disturbed by Wegener's explanation for how the continents moved apart.
Wegener explained his theory of continental drift based on the fact that the continents were moving through the ocean basins, and the continental crust was basically falling through this oceanic crust. Geologists at the time did not understand how the rigid, tough continental assemblies could plow through the weak oceanic basins, and still it was the continents that were deformed to make mountain ranges. That seemed rather peculiar.
According to Wegener, the mechanism behind continental drift was the centrifugal force of Earth's rotation and the tidal drag of the moon and sun. Geophysicists quickly and correctly exposed the flaws in this reasoning.
In fact, the most difficult aspect of this theory was that he alluded to a centrifugal force as explaining why, in fact, the continents drifted. It was shown quite conclusively that the forces were too small, the rocks were far too strong for this to have been the case. So people were able to reject this hypothesis completely at the time, based on a mechanism which, in fact, was shown to be incorrect.
Because Wegener's explanation for why continents drift did not hold up, he couldn't convince most other scientists that the continents had, in fact, ever drifted at all.
Some people like to say that scientists are so excited that they refuse to let any new idea come in. I think that's a bad way to think about this. We really are careful. And we don't want to leap on some glamorous new idea unless our data really does support it. Our understanding of how the world works really can incorporate it. So I think we really did not have any data that was so cutting and so clear that we had to set this theory. So I think they were actually being responsible, they were being conservative, but they were also being responsible scientists.
In 1930, Alfred Wegener died of a heart attack while attempting to cross the Greenland ice cap. But in the 1940s, with a lack of any conclusive evidence, the heated arguments about continental drift cooled off. Wegener's theory, however, would soon once again be propelled to the forefront of scientific debate, but in a most unexpected way.
In order to understand continental drift, we really needed to know how the oceans are made and destroyed. And we had very little understanding at all, even the shape of the seafloor. And so we really needed some new technology. Oceanographic methods are very driven by technology. And it turns out, I hate to admit anything was good about World War II, but it was very good for developing new technologies.
This new technology developed for World War II included the fathometer, an echo sounding device that instantly measured depth to the sea floor, enabling troop ships to move into shallow water. One transport commander, Harry Hess, made a habit of running his ship's fathometer continually. A geologist and Princeton professor in civilian life, Hess wanted to learn more about the topography of the seafloor. He soon discovered that the ocean floor was not level as expected, but was instead dotted with flat-top mountains which he named geos. Hess was perplexed by how these mountains formed. Their flat summits could seemingly be explained by wave erosion, but why then did the geos lie so deep underwater? Hess thought and saw a clue to this mystery when he observed that the deepest geos lay farthest from the mid-ocean ridge system. Hess and a colleague, Robert Dietz, suggested that geos are in fact wave-eroded islands which submerge as the crust beneath them subsides.
Keep at it.
To account for this subsidence, they proposed a radical new theory, which they called seafloor spreading.
Give it another shot.
Harry Hess had a bold, imaginative concept which he enunciated in 1962. It stated that the newly found Mid-Atlantic Ridge was actually the site of upwelling mantle beneath the ridge, and that it is solidified, solidified at the ridge, they were carried laterally, piggyback away from the ridge, much as rock and rock of the carried away by the central upwelling current. What Wegener had evoked was continents floating on as wide and drifting through ocean basins. What Hess and others showed was that the ocean basins themselves were growing from the mid-oceanic ridges, and that over the course of time they enlarged from the ridge, spread laterally. These would then be capable of carrying the continents initially much closer together as they were joined at the onset at the ridge, away from one another, as they went from one another by the spreading process. The combination of continental drift and seafloor spreading effect being both the mechanism and the manner and timing in which the continents had drifted apart from one another.
If mid-ocean ridges were continuously creating a new sea floor, it would seem that the Earth must be growing, swelling along the ocean ridges like a ball slowly being inflated. But scientists saw no convincing evidence for an expanding Earth. How then could the excess oceanic crust be explained? Hess suggested that the ocean floor simply sinks back into the planet and deep marine trenches. He claimed that this process, now called subduction, destroys the surface formed by seafloor spreading. Just as Wegener's hypothesis was weakened by lack of data, so too was the model of seafloor spreading. Hess cautiously referred to his own theory as the geopoetry, but supporting evidence coming from the emerging field of paleomagnetism.
Well, the term paleomagnetism refers to ancient magnetic fields of the Earth. You can learn about, you can say something about ancient magnetic fields of the Earth because of the record they leave in rocks. Many rocks become magnetized when they are formed, or sometime after they are formed. They become magnetized in parallel to the first magnetic field at that time. So if you can collect a rock sample, measure which way it's magnetized, and determine when it was magnetized, then you can learn about the orientation of the magnetic field at that time.
By the early 1960s, geologists were mapping the magnetization of rocks worldwide. One startling discovery came from the ocean bottom, where oceanographers discovered an unusual pattern of strong and weak magnetic stripes in seafloor bottom. Cambridge University student Frederick Vine and his advisor, Drummond Matthews, were especially intrigued. Two questions fascinated them. What causes the strong and weak parts of the magnetic patterns, and why is the pattern striped? They soon realized that the changing intensity of the pattern was caused by the reversal of Earth's magnetic field.
The evidence we have that the Earth's magnetic field has been reversed in the past is that on rocks, old rocks that are reversed magnetized, that is to say, they are magnetized pointing south rather than pointing north.
Yeah, it's good.
There was much scientific debate at first because it's known that some rocks can be placed in a magnetic field pointing one way and become magnetized in the exact opposite of that direction. The fact that such rocks existed meant it was possible that reversely magnetized rocks were simply a normal magnetic field. The clinching evidence came when scientists from the U.S. Geological Survey and from other places went on expeditions around the world, collected rocks of different ages, and were able to show that rocks collected from around the world of the same age always had the same polarity. Rocks that were younger than 700,000 years old were normally magnetized. Rocks older than 700,000 years were reversely magnetized. This global pattern of magnetic polarity recorded in the rocks is what indicates the magnetic itself changing polarity.
Vine and Matthews noted that the striped reversal pattern is parallel to mid-ocean ridges. By 1965, they concluded the best way to explain this relationship is by seafloor spreading. To check that conclusion, Vine studied the magnetic stripe pattern across several mid-ocean ridges. He predicted if seafloor spreading did occur, the magnetic pattern on one side of the ridge should be the mirror image of the pattern seen on the other. With startling precision, Vine's prediction proved correct.
Vine Matthews figured out this idea and published it as kind of an obscure paper to start with. But then when he said Vine connected enough profiles back to the American music and thought it really was too, he went on the road and was talking about it during one of the meetings. And in December of '66, gave a lecture at school, which was happening. That it changed the whole direction of life. I arrived here at the graduate student in January of 1967. I thought I was coming to this venerable old orthodox institute that everybody would be a little bit bored. And it was crazy. There were records strewn out on the floor all over the halls. Everybody was against all. It meant a a totally different way to explain almost everything on the seafloor.
A further test of the seafloor spreading hypothesis was carried out by geophysicists J. Tuzo Wilson and Lynn Sykes. They were interested in the faulting which offsets mid-ocean ridges. If a feature such as a road or a fence split and moved by an earthquake, one can deduce how the thrust shifted along the fault by measuring the direction of movement and the amount of offset. Many scientists expected the same to hold true at faults cutting across the mid-ocean